Hello there, Mr. Sutton here with the AB Calculus 310 homework solutions on derivatives of exponential functions. For this problem, they're telling us line L is tangent to the graph of y equals e to the x at the point k comma e to the x, and they want a positive value of k for which the y-intercept of this tangent line is going to be 1/2. So we're going to do two things here. First off, we're going to try to write the equation of this tangent line, and we're going to have some k's kind of mixed in there. And then we're going to figure out what we need to plug in to make the y-intercept of that line come out to 1/2. So let's begin. If we're going to get a tangent line, we need an x, a y, and a slope. Now they already told us the x and the y. That's k and e to the k. We don't know what k is. We're going to find it later, but that's going to be good enough for now. For the slope, we need to take the derivative of the original function, y equals e to the x, and then we need to plug in the x value k for that. So the slope of e to the x is just e to the x, and if I plug k in for x, I get e to the k. So e to the k is the slope. So for my tangent line, I can write y minus the y value e to the k equals m, my slope, which is also e to the k, times x minus x1, and x1 in this case is just the k value of this point, which is just k. Or the x value of the point, I should say, which is k. All right, so what do we do now? Well, we need the y-intercept to be 1/2, which means that this line here, whatever k is, it needs to go through the point 0, 1/2, if that's the y-intercept. So what I can do then is I can replace the x with 0 and the y with 1/2, and if I do that, that's going to leave me with only k as my only unknown here. So I'm going to have 1/2 for y minus e to the k equals e to the k times 0 minus k, and I just need to solve for k. Now, if you try doing this algebraically, you're going to have a tough time. I don't know that there is actually a way to do this one algebraically. Fortunately, as the answer choices make clear, this is a calculator question. So what I'm going to do instead is I'm just going to graph each half of this equation as its own sort of equation on a graph, and I'll see where they cross, and that'll give me the value of k. So here's my Desmos grapher window. Let me write one equation, y equals 1/2 minus e to the, and I'm not going to write k because it's going to ask me to put something in for k. I'm going to use x instead, only because that's what the grapher is expecting as the input variable. And let me also do y equals the second half of the equation, which I'll call e to the x, and then we'll use 0 minus x in there. So I end up with these two different equations, and I just need to see where they cross. Now, they could cross in lots of places, but the answer choices kind of give us some indication that we're looking for something between, say, 0 and 2. So let me zero in, or zoom in, between 0 and 2, and I see that there's this spot right here where they cross, and that's happening at the, this would actually be a k value now, of 0.768. So that's going to match up with answer choice B. For this problem, we're trying to take the derivative of e to the tan squared of x. So for this one, we're going to have to use the chain rule. So we start with the outer function, which is e to the something. So that derivative is going to be e to the something, so e to the tan squared of x. Now we take the derivative of the next function in. Now with tan squared of x, this is really tan of x, the whole thing squared. So squaring is the next function in. It's the next outer function. Derivative of something squared is going to be 2 times the something. So this is going to be times 2 tan of x. And finally, we have to take the derivative of tan itself, which is going to be secant of x, tan of x. Actually, no, it's going to be secant squared of x. There we go. So that's going to be answer choice. Let's see here. Let me just rewrite this in a slightly easier to read order. So 2 tan of x, secant squared of x, e to the tan squared of x. That's going to be answer choice D. To take this derivative, we're going to need to use the quotient rule. So let me set that up. I've got u prime v minus uv prime over v squared. That's the general setup. Now for my box and ribbon, to put all that together, I've got my numerator, e to the 2x, denominator of 2x, and their derivatives. So this is going to be e to the 2x times a tail of 2 because of that inner function of 2x. Derivative of 2x is just 2. Using the ribbon to put all that together, we've got, let's see, and I see that I've got to simplify this in the answer choices, so I'm just going to simplify as I go here because I know I'm going to have to do it at some point. So I've got 2e to the 2x times 2x. That's 4x e to the 2x. So that's my u prime v term right there. For u v prime, we're going back the other way. That's minus 2e to the 2x. And now for v squared, we've got 2x, the whole thing squared. So that's going to give us 4x squared down there. And at this point, let me go ahead and see if I can reduce this a little bit. To help me reduce it, I'm going to try factoring the numerator out a bit. So I notice that I can take out a 2 and an e to the 2x from both of these terms. Doing that leaves me with x. Actually, this is 2x right here. And then this term is just going to be 1. So 2x minus 1. And now I can cancel out the 2 and the 4, leaving me with just a 2x squared downstairs. Doesn't look like there's anything else I can really cancel out, though, so that was kind of anticlimactic. This is going to give me answer choice E. On this problem, I need the derivative of 10 to the x squared minus 1. So I'm going to need a chain rule on this, and this is a non-e base, so I'm going to have to use my b to the x times ln of b formula for derivatives in that situation. So let me start with the derivative of the outer function, which is 10 to the something. Derivative of that is going to be 10 to the something times the ln of 10. So that's my outer function derivative. Now I have to multiply by the derivative of the inner function of x squared minus 1. That's just 2x. And let's see here, did they simplify this at all? Well, there isn't really a whole lot we can do to simplify it. I can put the 2x and the ln of 10 out in front just to match one of the answer choices. That matches answer choice D, but beyond that, there's nothing else we can do. On this problem, we have a figure with the graph of g shown here, and a line tangent to the graph at x equals negative 1. H is the function given by e to the x times g of x. Based off of that, we want the value of h prime of negative 1. So we're taking the derivative of a product. Probably the product rule is a good way to go on this one. So u prime v plus uv prime. And to help set this up, I'm going to use my box and ribbon. So I have my two factors, which are e to the x and g of x. The derivatives of those, derivative of e to the x is also conveniently e to the x. G's derivative is g prime of x. At this point, though, they wanted me to plug in negative 1. I'm going to do that inside the box just to make things look a little bit nicer. So I've got e to the negative 1. I've got g of negative 1. Well, what's g of negative 1? I see here that I have the value negative 1 comma 3 on the graph of g. So that's going to be 3 for g of negative 1. And then we have another e to the negative 1 down there. G prime of negative 1, well, that's going to be the slope of this tangent line at x equals negative 1. And if I look here, I'm going, let's see, from negative 1 to 0, I'm going right 1, and I'm going down 6 from 3 to negative 3. So that's a slope of negative 6 that I can put in there. All right, let's use the ribbon to put it back together. I've got 3e to the negative 1 plus, or actually minus in this case because we've got a negative 6, so minus 6e to the negative 1. Now it just so happens that these are like terms, so I can actually just subtract here. I've got negative 3e to the negative 1. And that doesn't quite match any of the answer choices, but I know I can rewrite this as negative 3 over e, just applying my negative exponent rule. So that's going to be answer choice B. For this problem, which is kind of an oddball problem, we're given the function y equals e to the n times x, and presumably x is the input variable and n is treated as a constant here. They want the derivative, the nth derivative of this term. So they didn't tell us which derivative they wanted, they just want the nth derivative. Well,
let's take a few derivatives and see if there's some pattern we can pick up on. And you'll notice that there's an n in all of these answer choices, so we have to figure out what we have to do with n to get the nth derivative. Let's start with the first derivative, y prime, dy over dx. That's going to be e to the nx, so that we're using the chain rule here. This is the derivative of the outer function, e to the something, times the derivative of nx, the derivative of the something. So that's just going to be the constant n, which we could rewrite as n e to the nx. All right, let's do the second derivative now. So that's going to be this first derivative, taking the derivative of this. That's going to be n e to the nx times another n, because of the chain rule there. So that would actually be n squared e to the nx. And let's do just one more derivative, just so we have enough data to come up with a pattern here. Third derivative now. Well, that's going to be the second derivative's derivative. So we have n squared e to the nx times another n, because of the chain rule. So that's n cubed e to the nx. So I think there's definitely a pattern here. It looks like the order of the derivative is matching the exponent on the n, because every time you take another derivative, you keep multiplying by another n. Otherwise, everything else is unchanged. For the nth derivative then, this ought to be n to the n e to the nx, which is going to match, let's be careful about this because these all look kind of the same, answer choice A. On this problem, we're given this crazy expression, and we want to know the value of dy dx at the point 2, 2. So we're going to have to take the derivative of this thing, and since y is kind of tough to isolate, we're going to have to use implicit differentiation. Then we're going to have to plug 2, 2 into whatever crazy equation we get out of this. So let's get started. Going from left to right, derivative of e to the x is e to the x. Derivative of negative y, that'll be negative 1 dy over dx, because we're imp diffing here. So y is treated as an inner function with a chain rule attached every time. Equals, well, now we have to use the product rule for this xy cubed term. So I have a factor of x and y cubed. And the derivatives of these are going to be, for x we've got 1, and for y cubed, this is going to be 3y squared times dy over dx. So using the ribbon to multiply that out, we've got, this is going to equal y cubed, 1 times y cubed, minus 3xy squared dy over dx. And then we have derivative of e squared. E squared is actually a constant, so that derivative is 0. So is the derivative of 18. So although this equation looks kind of crazy, we differentiated away a lot of stuff. All right, so at this point, we're going to go back and put all the dy dx's together. So I've got this negative dy over dx that can stay on the left side. And I'm going to subtract this 3xy squared dy over dx to get it over to the left side. On the right side, we have the y cubed that was already there, and we're going to subtract this e to the x to get it over there as well. All right, now on the left side, I can factor out a dy over dx. That'll leave me with negative 1 minus 3xy squared inside that parentheses. And then I'll just divide by negative 1 minus 3xy squared to get dy over dx by itself. At this point, I have to plug in 2, 2. All right, so evaluating this derivative at 2, 2, we've got the y value of 2 cubed minus e to the x value 2. Down here we have negative 1 minus 3 times the x value 2 times the y value of 2 that's being squared. And we have to simplify this because we're matching an answer choice. Upstairs we have 8 minus e squared. Downstairs, this is negative 1, and let's see, this is going to be, 3 times 2 times 4. That's going to be negative 1 minus 24, so negative 25. That does not, in fact, unfortunately, match any of the answer choices. The only one with a 25 in it is choice C. And in fact, if you change all the signs in this fraction, which we're allowed to do because you're basically multiplying by negative 1 over itself, we end up with e squared minus 8 over positive 25, so just reversing all the signs in a fraction, and that does match answer choice C. On this problem, we're given the function e to the x, and we want to know which of these is equivalent to the derivative of e of this function. All right, so basically we're trying to convert this into the limit form of a derivative. Let's start with the general formula for that. They're using Newton notation, it looks like. So we're going to have the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is definitely a good one to have in your back pocket, ready to go at any time. Now in this problem they want f prime of e. So I'm going to just replace all these x's with e's. So I've got f of e plus h minus f of e. All I have to do now is actually apply the f function to e plus h and e. So over here, instead of writing f of e plus h, I can write e to the e plus h. And here, instead of writing f of e, I can write minus e to the e. So we're just plugging e plus h and e into the f of x function here. And does this match any of my answer choices? So it looks like this is going to line up with answer choice E, ironically. So there you go.
For this problem, they're saying f is 3 times e to the 2x and g is 6 times x cubed. They want to know at what value of x do the graphs of f and g have parallel tangent lines. So if the tangent lines are parallel, that means that there is some x value that when I plug it into the derivatives of each of these functions, it should give me the same value. So the way to solve this then, I just need to figure out the derivative of these two things, set them equal, and solve for x. So the derivative of f of x, we're going to need the chain rule on this one. The derivative of 3 times e to the something is 3 times e to the same something, which in this case is 2x. But now we have to multiply by the derivative of the something of the 2x, and that's going to be 2. For g prime, we're just going to have a power rule here. This is just 18x squared, so nothing crazy going on there. And now I just need to see where f prime and g prime equal each other. So I don't want to try to do this algebraically. I don't think there really is a clean way to do it algebraically, so I'm going to use the grapher instead. So here's my Desmos window. Let me create two equations. So we'll say y equals, and I can simplify this a little. We'll call this 6e to the 2x. And then let me do also y equals 18x squared. So we've got f prime and g prime. And if I just move in here a little bit, and for the x values that I'm looking for, notice all the answer choices are negative, and like between negative 1 and 0. So I'm looking somewhere in this area, and I see that there's this one right up here where we're crossing. This is happening at negative 0.391 if I round that off. So right there. So that's the x value that I actually need, and that's going to be answer choice C.
On this problem, we're just trying to find the derivative of this function here. So this one could potentially be a slightly nasty chain rule, not too bad, but there's definitely a way to save some time and be a little bit clever on this one. Using our log rules, we know that we're allowed to pop in this 3 outside the log as an exponent on the stuff inside. So this we could rewrite as just ln of x to the 2nd to the 3rd, or x to the 6th, if you wanted to simplify that. We also know that e and ln cancel each other out when there's nothing in between them, because ln is just the thing I have to raise e to get all this stuff. If I go ahead and raise e to the thing I need to raise e to get all this stuff, I just get all this stuff. So this ends up coming out then, when these cancel, to just x to the 6th. And now we just have to take the derivative of that, which is just using our power rule, 6x to the 5th, which conveniently matches up with answer choice E. Now, you could have used the chain rule on this, but you would have had to have simplified it a bit to get this answer choice. So simplifying with log rules before using any kind of derivatives is usually the way to go.